Question 486. Suppose the function f is continuous for all x, and we are given the following table of values for x and f of x. With all the points in this partition, approximate this definite integral by using left-hand Riemann sum. Remember, this definite integral is the net area between a function and the x-axis. And the Riemann sum uses the area of a series of rectangles to approximate this definite integral. Here, I will show you two different ways to find the Riemann sum when the table is given. The first way is to draw a rectangle on the coordinate plane. Let's plot these coordinates on this coordinate plane first. So we have 0, 4, 1, 2, 3, -2, 6, 1. Right? For the left-hand Riemann sum, we have to find the sum of areas of rectangles drawn from the point on the left-hand side at each interval. So, at this interval from 0 to 1, the rectangle must be drawn from this point, the point on the left, like this. Okay? At this interval right here, the rectangle has to be drawn from this point, the point on the left. At this interval right here, we have coordinate right here, right? So the rectangle has to be drawn like this. Okay? So this definite integral f of x dx can be approximated as, using the left-hand Riemann sum, the areas of sum of areas of these three rectangles. That's going to be 1 times 4, right? 1 times 4 plus 2 times 2, 2 times 2 plus 3 times -2, right? 3 times -2. So that is equal to 4 plus 4 minus 6, right? So that's going to be equal to 2, right? So far so good. A second way to find the left-hand Riemann sum is to look at the table and write the area of rectangles. As you may have already noticed, the value of the height of the rectangle is the function value of the left point of each interval. So in this interval, the height of the rectangle is 4. In this interval, the height of the rectangle is 2. In this interval, the height of the rectangle is -2. Does that make sense? So by looking at this table, we can just write this definite integral can be approximated using the left-hand Riemann sum as 1 times 4 plus 2, 1 to 3, that's 2, right? Times the function value on the left, 2 times 2, plus 3 times -2, 3 times -2. So that's going to be equal to 2, right? So we can find the Riemann sum in these two ways. All right? Question 487. We're going to approximate this definite integral by using right-hand Riemann sum this time. The first way is to draw the rectangles on the coordinate plane. For the right-hand Riemann sum, the rectangles must be drawn from the point on the right-hand side at each interval. Okay? Let's try that. We have 4 coordinates again, right? At this interval right here, we have 2 coordinates, 0, 4 and 1, 2. For the right-hand Riemann sum, we have to draw a rectangle from the point on the right-hand side. So from this point right here, just like this. At this interval right here, we have to draw the rectangle from this point right here. So just like this. At this interval right here, we have to draw a rectangle from this point right here. So just like this. Okay, so this definite integral 0 to 6 f of x dx can be approximated by using right-hand Riemann sum as 1 times 2 plus 2 times -2, right? 2 times -2 plus 3 times the height is 1, right? So 3 times 1. So that is equal to 2 minus 4 plus 3. That's going to be equal to 1. Okay? Or just by looking at this table right here, this definite integral can be approximated using the right-hand Riemann sum as this interval times the point on the right-hand side, the function value on the right-hand side. So 2, right? So 1 times 2 plus 2 times -2, 2 times -2 plus 3 times 1, 3 times 1. So that's going to be equal to 1. Okay? Question 489. Suppose the function f is continuous, strictly decreasing, and concave down for all x. The table above gives values of f at selected values of x. Approximate this definite integral by using a midpoint Riemann sum with the 2 equal subintervals. Is this approximation an overestimate or an underestimate for this definite integral? Here we have a table and an xy plane with the coordinates plotted. First, we're going to approximate this definite integral by using 2 midpoint Riemann sum with the 2 equal subintervals. Each subinterval must be from x equals 0 to 4 and 4 to 8, right? Which are 2 equal subintervals, right? In a midpoint Riemann sum, the height of each rectangle is equal to the value of the function at the midpoint of its subinterval. So for this subinterval, the midpoint is 2, right? Then the height must be this function value, which is equal to 9. For this subinterval, the midpoint is 6. So the height of the rectangle must be equal to this function value, which is equal to 4. Does that make sense? Now let's approximate this definite integral by using a midpoint Riemann sum. So this definite integral from 0 to 8 f of x dx is equal to, for this subinterval, midpoint is 2. So we have to draw from a rectangle from this point right here, like that. And for this subinterval, midpoint is 6. So draw a rectangle from this point right here. So this is going to be 4 times the height, 9, right? Height 9. 4 times height is 4, right? So 4 times 9 plus 4 times 4. So that's going to be equal to 4 times 9, 36, plus 4 times 4, 16. So that's 52, right? Or by just looking at the table, we can write 4 times the height, 9, right? The midpoint is 2. So this function value is the height. 4 times midpoint is 6. So the height 4. 4 times 9, 4 times 4. Just like this. Okay? We have one more question here. Is this approximation an overestimate or an underestimate for this definite integral? Since f is continuous, strictly decreasing, and concave down, then if we use midpoint Riemann sum, that's going to be overestimate, because if a function is concave down, the graph of f looks like that, right? So let's say this is one subinterval. Okay, if we use midpoint, let's say this is a midpoint, and if we draw the rectangle, right here, this is our approximation, right? This area. And as you see it, this approximation is greater than the actual area under this curve, right? Which is the definite integral, right? So if f is concave down, and if we use midpoint Riemann sum, that's gonna be overestimate for this definite integral. Okay? Question 490. Approximate this definite integral by using two trapezoids of equal subintervals. Is this approximation an overestimate or an underestimate for this definite integral? This time, we're going to approximate this definite integral by using trapezoid rules. It says two trapezoids of equal subintervals, right? So each subinterval must be from x equals 0 to 4 and 4 to 8, right? Now what we need to do is we need to draw two trapezoids. So from 0 to 4, so draw straight line segment from here to here. That's one trapezoid. And draw another line segment from here to here, right? Well, the base when x is equal to 8 is equal to 0, right? So this is actually triangle, okay, since this is a 0. Okay, so let's find the area of these two trapezoids that approximate this definite integral. So integral from 0 to 8 f of x dx is going to be approximated using the area of sum of area of these two trapezoids. Well, this one is actually triangle, right? We know that from geometry, the area of a trapezoid is the sum of two bases, right? Sum of these two times height times 1/2, right? The first trapezoid is equal to 1/2 times the height is 4. Height is 4 times the sum of two bases. That's 10. And the height here is 7, right? So 10 plus 7 plus the second one is actually triangle. 1/2 times the height 4 again. 4 times sum of two bases. That's gonna be 7 plus 0. This is a 0, right? So that's gonna be, that's 2 times 17, 34, plus 2 times 7, that's 14. So that's gonna be equal to 48, right? There is one more question here. Is this approximation an overestimate or an underestimate for this definite integral? Okay, if a function is concave down, the graph of f looks like that, right? Then if we draw trapezoid, by drawing line segment here, that's going to be underestimate, right? Because the area of trapezoid is only this, but definite integral is the area under this curve, right? So when f is concave down, our trapezoid is underestimate. What if f is concave up? Let's say we have concave up like this. Then our trapezoid will be overestimate, right? If we draw a line segment like this, our trapezoid, the area of trapezoid is overestimate because that's greater than the actual area under this curve, right? So the answer for this question is an underestimate for this definite integral since the function is concave down. Question 491. Is the approximation from left-hand Riemann sum an overestimate or an underestimate for this definite integral? Whether the left or right Riemann sums are overestimated or underestimated depends on whether the function is increasing or decreasing. For this problem, function f is strictly decreasing, right? When a function decreases, the left Riemann sum is always overestimated. If we draw the function, we can easily figure it out. Let's draw the function f, decreasing function like this, with the two subintervals, like that. If we draw the rectangle from left-hand side, which means left-hand Riemann sum, right? Like that. This rectangle, the area of rectangle is always overestimate for the definite integral, right? Which is greater than the area under this curve, right? What if the function is increasing? Let's draw another function, increasing function like that. If we have two subintervals like that, and let's draw the rectangle from left hand side, from here to here, here to here. As you see it, the area of rectangle is less than the actual area under this curve, right? So when function increases, the left-hand Riemann sum will be underestimated, right? So the answer for this question must be overestimate because the function is decreasing. Question 492. Is the approximation from right-hand Riemann sum an overestimate or an underestimate for this definite integral? As we talked about this in the previous problem, it depends on whether the function is increasing or decreasing. If the function is increasing like this, then right-hand Riemann sum will be overestimate, right? Because we'll have these rectangles. The area of these rectangles will be greater than the area under this curve, right? So if the function increases, right-hand Riemann sum will be overestimate, right? If the function decreases, like that, then right-hand Riemann sum will be underestimate, right? Because we are gonna have this area, the sum of these two rectangles, which is less than the area under this curve, right? So it'll be underestimate for the definite integral. In this case, function is strictly decreasing, right? So our right-hand Riemann sum for this integral will be underestimate, all right?